Okay, we're talking about reliable communication on noisy channels. Previously we had this diagram. Where a message was sent in this end, was encoded in some alphabet SX. Decoded, the channel outputs were represented in some alphabet possibly different, called SY. And finally, the decoder gave us some estimate W hat. And the question is the estimate W hat equal to the original message sent? That's really what we want. That's what we mean by reliable communication. And we want to make that probability as close to 1 as possible. So last time we introduced mutual information, IXY, and what I said was the capacity of a channel is the maximum over all possible input distributions of that mutual information. Let's show one final example of mutual information before we start on what we're going to talk about today, which is to basically introduce the important definitions and mathematical machinery we need to prove that this statement is true. So I just presented that statement without proof. So last time we saw examples of the noiseless channel. That had capacity of 1, where SX and SY were both binary, so that makes sense. SX is, for each channel use, we have 1 bit. At the output, we have 1 bit, so it makes sense that we could transmit 1 bit reliably. We saw the erasure channel. So remember what that was. If I put in a binary bit, I get out either exactly that bit or a symbol I called E, which represents the fact that whatever bit I put in was erased. The capacity of that channel we showed is 1 minus PE, where PE is the probability of erasure. Let's look at one other, so the noiseless channel is trivial. The erasure channel is probably the simplest non-trivial channel. Let's look at one other very important channel. Called the binary symmetric channel. So in the binary symmetric channel, my input alphabet is binary, my output alphabet is binary, and basically representing this on a graph, here's my inputs, here's my outputs. Each input can possibly cross over like this. It's called symmetric because the probability of crossover is the same regardless of which bit is input, so let's call it P. So given an input 0, I get an output 0 with probability 1 minus P, or it flips with probability P. Similarly, an input 1 flips with probability P, or it does not flip with probability 1 minus P. So, mutual information for this channel is, let's write it in this form, H of y minus h of y given x. So first let's write h of y given x. Y given x is the sum over x and y, excuse me, sum over x, p of x, sum over y, p of y given x, times log 1 over p of y given x. I'm going to write this sum under y as follows, sum over x, p of x, times, so I have two possibilities for y. The possibilities for y are where y is equal to x and where y is not equal to x. So x is binary, y is binary. So one of the two values of y must be equal to x and the other one must be not equal to x. So let's write out both terms explicitly. Probability of y equal to x given x, log 1 over probability y equal to x given x, plus probability y not equal to x given x, log 1 over probability y not equal to x given x. So remember that this is my diagram representing what's going on in the channel. So if I know what x is, what's the probability that y is not equal to x, regardless of whether x is 0 or 1? It's p. So if x is 0, then it becomes 1 with probability p. If x is 1, it becomes 0 with probability p. So this is equal to, excuse me, that's this term. Probability y is not equal to x. So that's p log 1 over p. Similarly, the probability that y is equal to x is 1 minus p, regardless of whether x is 0 or 1. So this is equal to the sum over x, p of x, times 1 minus p log 1 over 1 minus p, plus p log 1 over p. Now you'll notice nothing inside these brackets depends on x anymore. So now I have the sum over x, p of x, times this constant. Sum over all possible x of p of x is just 1. So this is equal to 1 minus p log 1 over 1 minus p plus p log 1 over p. So that's regardless of the distribution of x. Remember last time we defined the function h of p, little h of p, is p log 1 over p plus 1 plus p, or excuse me, 1 minus p, log 1 over 1 minus p. So therefore this is little h of p. Now it's worth pointing out that if I had a random sequence that was 1 with probability p and 0 with probability 1 minus p, this would be its entropy. So in particular, if I had a random sequence that was a 1 whenever 0 was flipped to 1 or 1 was flipped to 0, or a 0 when no flip occurred, then this would be the entropy of that sequence. So in some sense, this is the entropy of the noise. In fact, you can think of the binary symmetric channel as an additive noise channel in the following sense. So y, the channel outputs, can be thought of as x plus n